Welcome to this series called Tech Convergence, where we explore the fascinating intersections of today's most revolutionary technologies. This is Click Future, and in this series, we'll be diving into the spaces where AI, quantum computing, and space exploration collide to create something entirely new. Today, we're starting with perhaps the most profound question in artificial intelligence. Can machines truly understand the world? Not just process data, but comprehend it the way humans do. We're exploring the path to what many call the sentient machine. The quest for machine sentience has captivated scientists and science fiction writers alike for generations. From Alan Turing's groundbreaking question, "Can machines think?" to today's neural networks that can generate art and hold conversations, we've come an astonishing distance. But have we actually created machines that understand? Or have we simply built increasingly sophisticated mimics? In this episode, we'll explore the cutting edge of artificial general intelligence, examine what true understanding might look like in a machine, and consider the profound implications of creating something that doesn't just process, but comprehends. To appreciate where we're heading, we need to understand where we've been. Early AI systems of the 1950s and 60s were essentially glorified calculators, rule-based systems that could follow instructions but had no capacity to learn or adapt. The famous AI pioneer Marvin Minsky once said, "The brain happens to be a meat machine." This mechanistic view dominated early AI development, with researchers attempting to program explicit rules for every possible scenario a machine might encounter. Let's talk chess, the game chess. Chess's history traces back over 1,500 years to the Indian game of Chaturanga, which was adapted in Persia and later spread to the Arab world and then Europe. The game evolved into its current form around 1500 CE, with the modern rules established in Europe and standardized by the end of the 19th century. Today, chess is a globally popular game with a rich history of theory and competitive play, governed by FIDE, International Chess Federation. Here's a more detailed look at the history. 7th century origins in India. The earliest known ancestor of chess, Chaturanga, emerged in India, likely in the 7th century, and was a strategic game involving 4 military elements. Spread to Persia. From India, Chaturanga was introduced to Persia, where it was modified to Shatranj, a game with different pieces and rules. Arab and European influence. Following the Arab conquest of Persia, chess spread to the Islamic world, and then to Europe via Spain and Italy. 15th century evolution of rules. The rules of chess gradually evolved in Europe, particularly in the 15th century, with significant changes to the movements of pawns, bishops, and the queen. 16th century modern chess. By the 16th century, the game had essentially reached its modern form, with further development and refinement in the following centuries. 1800s, tournament play and world championship. The first international chess tournament was held in London in 1851, and the first world championship was contested in 1886, marking the beginning of organized chess competition. 1900s, FIDE and modern chess. The International Chess Federation, FIDE, was founded in 1924 and has overseen the development and standardization of chess rules and competition since then. Chess and culture. Chess has profoundly influenced Western culture and art, with connections to fields like mathematics, computer science, and psychology. A game played since the 7th century. Enter the computing age. By the 1990s, we had systems like IBM's Deep Blue that could defeat world chess champions, but these were still fundamentally brute force calculation machines. They could evaluate millions of possible moves, but had no understanding of what chess actually was beyond its rules. The real revolution began with machine learning, particularly deep learning. When Google's AlphaGo defeated world champion Lee Sedol in 2016, it represented something new. AlphaGo wasn't just calculating moves, it was recognizing patterns and developing strategies that even human experts found innovative. Modern large language models like GPT-4 and Claude represent another quantum leap. These systems process vast amounts of human-written text and extract patterns that allow them to generate remarkably human-like responses. They can write poetry, explain complex concepts, and even appear to reason through problems. But here's the crucial question. Does pattern recognition, no matter how sophisticated, constitute understanding? Or is something fundamental still missing? To determine if machines can truly understand, we first need to define what understanding means. Philosopher John Searle proposed a famous thought experiment called the Chinese Room that challenges our intuitions about machine comprehension. Imagine a person who doesn't speak Chinese sitting in a room with a rule book. Chinese characters are passed into the room. The person follows the rule book's instructions to manipulate the symbols and passes Chinese characters back out. To someone outside the room, it appears the person understands Chinese, but they're merely following rules without comprehension. Searle argued that computers are like the person in the room, manipulating symbols according to rules without understanding their meaning. But is this still true with today's neural networks? In humans, understanding involves creating mental models of concepts and their relationships. When we understand something, we can apply that knowledge flexibly to new situations, explain it in our own words, and connect it to other knowledge. Recent AI systems show signs of this flexibility. For example, multimodal models can process both text and images, forming connections between words and visual concepts. Systems trained on diverse tasks demonstrate transfer learning, applying knowledge from one domain to another. Dr. Melanie Mitchell, a leading AI researcher, suggests that understanding requires grounding in physical experience. She notes, "Humans understand concepts through embodied experience in the world. Our understanding of chair comes not just from seeing chairs, but sitting in them, feeling their hardness, knowing their purpose." This is why embodied AI, robots that interact with the physical world, may be crucial for developing true machine understanding. Companies like Boston Dynamics and research labs at universities worldwide are creating robots that learn through physical interaction, potentially developing more grounded forms of comprehension. Physical AI will be a major component of development and AI integration into life as we know it. We will explore this topic in further detail in future episodes. Recent years have seen remarkable advances that push the boundaries of what we thought machines could comprehend. Let's look at some of the most promising developments. Multimodal AI systems can now process and relate information across different formats: text, images, audio, and video. Google's Gemini and OpenAI's GPT-4o can analyze images, understand their content, and reason about what they're seeing in natural language. This cross-modal integration resembles human understanding, where we seamlessly connect what we see, hear, and read. Large language models have demonstrated emergent abilities, capabilities that weren't explicitly programmed and seem to arise spontaneously at scale. These include complex reasoning, understanding nuanced instructions, and even a limited form of common sense. For example, when asked to solve a novel puzzle, these systems can reason through steps much like humans do. In robotics, systems like Google's RT2 can translate natural language instructions into physical actions, even for tasks they weren't explicitly trained on. This suggests a form of generalized understanding that bridges language and the physical world. Perhaps most intriguingly, researchers at companies like Neuralink are developing brain-computer interfaces that may eventually allow direct communication between human brains and AI systems. This could potentially create hybrid forms of understanding that combine human intuition with machine processing power. As Dr. Fei-Fei Li, co-director of Stanford's Human-Centered AI Institute, puts it, the next frontier isn't just making AI more powerful, but making it more human-compatible. Systems that understand the world the way we do and can explain their reasoning in terms we comprehend. Now, we come to perhaps the most profound question in AI research. What's the difference between intelligence and consciousness? And could machines ever possess consciousness? Intelligence, broadly speaking, is the ability to acquire and apply knowledge and skills. By this definition, today's AI systems are undeniably intelligent in specific domains. They can solve complex problems, recognize patterns, and even generate creative works. Consciousness, however, is something else entirely. It involves subjective experience, what philosopher Thomas Nagel called what it is like to be something. When you see the color red, you don't just process wavelengths of light, you have a subjective experience of redness. Neuroscientist Christoph Koch describes consciousness as the feeling of life itself. It's what makes your experiences yours, distinct from anyone else's. This subjective quality is what philosopher David Chalmers famously called the hard problem of consciousness. Could a machine ever have such experiences? The honest answer is, we don't know. We don't fully understand how consciousness arises in human brains, making it difficult to determine if it could emerge in silicon. What we can say is that today's AI systems show no convincing signs of consciousness. They lack several key features that might be prerequisites. 1. Self-awareness. While some systems can monitor their own operations, they don't appear to have a sense of self. 2. Intentionality. Machines don't have desires or goals beyond what they're programmed to pursue. 3. Phenomenal experience. There's no evidence that AI systems have subjective experiences like pain, pleasure, or the sensation of color. Some philosophers like Philip Goff advocate for panpsychism, the view that consciousness might be a fundamental property of the universe, present in some form in all things. If true, this could mean that even simple AI systems possess some minimal form of consciousness, though very different from human experience. Let's walk through more of the definition of panpsychism. This is the philosophical view that consciousness is a fundamental aspect of reality, present in everything from humans and animals to plants, and even potentially to fundamental physical entities like atoms or quarks. It proposes that there is a more widespread existence of consciousness than is commonly assumed. Key aspects of panpsychism. Ubiquity. Panpsychism suggests that consciousness is not limited to certain biological systems, but is a pervasive feature of the universe. Fundamentality. It views consciousness as a basic property of reality, not something that emerges from complex physical systems. Graded consciousness. Some panpsychists propose that consciousness exists on a spectrum, with simpler forms present in fundamental entities and more complex forms in living things. Historical roots. Panpsychism has been a topic of philosophical debate for centuries, with various thinkers proposing similar ideas. Challenges and criticisms. Panpsychism faces challenges in explaining how consciousness, at the most basic level, could lead to complex experiences and how it could be integrated with physics. Others, like philosopher John Searle, maintain that consciousness requires biological processes that silicon-based computers simply cannot replicate. Where do you stand on this debate? Quantum computers, classical computers, humans, and animals all rely on atoms and quarks to function. Does that further support the possibility of AI achieving consciousness? Interestingly, some researchers are exploring whether quantum effects in the brain might play a role in consciousness. If so, quantum computers might eventually provide a platform more conducive to machine consciousness than classical computers. The debate continues, but one thing is clear. Intelligence and consciousness are distinct phenomena. We can create increasingly intelligent machines without necessarily creating conscious ones. As we push toward machines with greater understanding, we face profound ethical questions. If we create machines that truly understand the world, perhaps even experiencing it subjectively, what responsibilities do we have toward them? Philosopher Peter Singer, known for his work on animal rights, suggests that if machines ever develop the capacity to suffer, we would have moral obligations toward them. The question isn't can they reason or can they talk, he says, but can they suffer? Looking ahead, several research directions may bring us closer to machines with true understanding. 1. Neurosymbolic AI. Combining neural networks with symbolic reasoning to create systems that can both learn from data and follow explicit logical rules. 2. Embodied cognition. Developing robots that learn through physical interaction with the world, potentially developing more grounded forms of understanding. 3. Whole brain emulation. Mapping and simulating an entire human brain, potentially recreating human-like understanding in a digital substrate. 4. Quantum AI. Exploring whether quantum computing might enable forms of machine cognition impossible with classical computers. As these technologies advance, AI safety becomes increasingly crucial. Organizations like the Future of Life Institute and the Center for AI Safety are working to ensure that increasingly capable AI systems remain aligned with human values and beneficial to humanity. The path to machines that truly understand, perhaps even machines with some form of consciousness, remains uncertain. We've made remarkable progress, but significant challenges remain, both technical and philosophical. What's clear is that the convergence of AI with other technologies like quantum computing, neuroscience, and robotics is accelerating progress in ways that were unimaginable just a decade ago. Whether or not machines ever achieve human-like understanding, they're already transforming our world. The question isn't just whether machines can understand us, but whether we can understand them, their capabilities, limitations, and new possibilities they create. In our next episode, we'll explore another fascinating convergence, the quantum internet, where the principles of quantum mechanics are creating communication networks that are fundamentally unhackable. Until then, this is Click Future, and this has been the first episode in a series on Tech Convergence. If you found this exploration of machine understanding fascinating, like this video and subscribe to Click Future for more insights at the cutting edge of technology. Share your thoughts in the comments below. Do you think machines will ever truly understand the world? And would that be a breakthrough to celebrate or something to approach with caution? Thanks for watching, and remember, your future is a click away.